Alright, so some of you have been asking about um, the graph, how to work on the graph. So I'll just show you how to deal with that. I'll take the example from class that you started working on, and then from that you should be able to deal with the other graph. So the question is the vapor pressure of dichloromethane is measured as a function of temperature, and the results are tabulated. So determine the heat of vaporization of dichloromethane from the results. So I will show you the results in the next slide. So what do you do here? You are given temperature in Kelvin and vapor pressure in torr. So the first thing is to change the temperature to 1 over temperature. So you are changing it to 1 over temperature here. And you want to change the vapor pressure from torr to the natural log of vapor pressure. So if we take the natural log of 0.8, the answer will be minus 0.2. If you take 1 over 200 for 1 over t, the answer will be 0.0050. If we do the same thing, the natural log of 4.5, we find that it is 1.5. 1 over 220, we find that it is 0.0045. If you keep on repeating this process, this is what we get for all the values. So we are starting with minus 0.2 here all the way to 6. Here we are starting with 0.0050 all the way down to 0.0026. So just looking at the data that we have, is that we are going to have a descending graph or a decreasing graph. Now, in terms of your scale, you want to make your graph in such a way that the scale is big enough. You want to cover about 3/4 of your scale or of your graph. So that's what we are going to try to do in this case. And remember, our aim is to determine the enthalpy of vaporization. So to do that, we plot a graph. We plot a graph of natural log of P versus 1 over T. That's the graph that we plot. So it will be this data as the y-axis and this data as the x-axis. So this is y-axis, and this one is x-axis. And we'll try to make sure that the scale is really good. So from this graph, what we are looking for is the slope of the graph, and I'll talk about that. Our delta H, which is the enthalpy, will be given by negative R times the slope of this graph. So we'll come back to that when we find the slope. Now this is the data. Let me show you what we are going to do with the data on the graph. Now this is our graph paper. So the first thing we are thinking about is the scale. So how is the scale like? Y-axis, the scale starts from minus 0.2 all the way to 6.0. That is the natural log of pressure. X-axis, the scale starts from 0.026 all the way to 0.005. Now, when making a graph of this type of scale, you want your 0.005 to be somewhere between, because that's the x-axis. You want 0.005 to be somewhere between here, or at least 0.005, which is the last of the values, should be close to this end. So you want to use much of the graph as much as possible. In this case, this 6, that's the highest y-axis. You want it to be towards the end here. The 6 should not be here. It should be all the way towards the end. So that in terms of using your graph, you are making sure that you have used all the way from here, 3/4 of the graph. So what we are saying is you want your graph to take all this part. You want your graph to take all this part. You don't want your graph only to be from here to here. No, you don't want that. You want your graph to take about 3/4 of the graph paper. So, which means your scale, you need to make sure that the scale covers this whole area of the graph. Now, how do we go about it? So, if we look at our scale again, our data, the natural log p, we start with minus 0.2, 1.5, 3.0, 4.3, 5.3, and 6.0. While the 1 over t, we have 0.0050, 0.0045, 0.0042, 0.0038, 0.0036, then 0.0026. So that is our, so this is the y-axis, this is the x-axis. Now the scale of the x-axis, because we want 6 to be somewhere here, we need to make sure to make the scale big enough. So let's say I will start here. For now, I will ignore this negative. I'll just deal with the positives. So if I start here, this is, I'll give it 0. Then I'll count, because I want a big scale, 1, 2, 3, 4. So this will be 1. Then I count 1, 2, 3, 4. This will be 2. 1, 2, 3, 4. This will be 3. 1, 2, 3, 4. This will be 4. 1, 2, 3, 4. This will be 5. 1, 2, 3, 4. This will be my 6. So I'm making sure that I go all the way to 6 and I cover most of the graph paper. What about the 1 over t? So this one is natural log pressure, the y-axis. Now this part is 1 over t. So the units for this one are Kelvin to the power -1. Now here I want to move from 0.0026 to 0.50. So if I want, let me say I will start from, let me just check something. If I start from 0 here, if this is 0, then 1, 2, 3, 4. This would be 0.001. So each 4 is a 001. 1, 2, 3, 4. This one is 0.002. 1, 2, 3, 4. This one is 0.003. 1, 2, 3, 4. 0.004. 1, 2, 3, 4. 0.005. 1, 2, 3, 4. 0.006. So I've made sure to use most all of this graph. Now once I do that, I need to start plotting my lines. As I said at the beginning, I am going to, for now, I am going to ignore this, at least for now. If I need to use it later, I can. For now, I'm going to ignore that and work with the positives, because What I'm looking for is just a straight line. So if I start working with 1.5, so I'll start from here. This is 0, 0, 2, 5. Each division here is a 0.25. So if I want to go to 1.5, 1.5 is somewhere here. This is 1.5. And 1.5, what I'm going to do is I'll make a line on 1.5 all the way to where I want to go. So I'll make a line. You can make a dashed line like the line I'm making here. And then you say for 1.5 I have 0.045. So you come here, say where is 0.045? So 0.045 is here. So I'll make, you make your line using a pencil. Where the two lines intersect, you make a point there. So I'm done with this one. Now I'm going to 3. Where is 3? 3 is here. So I'll follow 3. I'll draw dashed lines. Draw lines that you can erase afterwards. I'll draw dashed lines here. And for 3, we have 0.0042. So each point here is like 0.00025. That's what each point is. So if I want to go to 4.2, if this is 4.5, this is 0.0045, which means this is 0.00425, and that makes 0.042 to be somewhere here. So this will be my line I'm drawing if I want, and the line is going to intersect here between 4.2 and 3. So this is my second line. I'm going again to 4.3. Where is 4.3? So this part is 4, this is 5, 6. So if this is 4, this is 4.25. Somewhere here should be 4.3. So I'll draw a line along 4.3, a horizontal line. So 4.3 goes with 0.038. So I'll look here. Where is 0.038? If this is 0.04, this is 0.00375. So 8 should be somewhere here. So I'll draw a line here that goes all the way. Make sure that you are using a ruler. Where the lines intersect, you have your point. Now I'll go to 5.3. So 5.3 is also somewhere here. So I'll draw a line here all the way. Your lines will be good because you are going to use a ruler. And then this one goes with 0.0036. So this is 0.0035. That's this line. So 36 should be somewhere here. So I'll draw a line here. Where the lines intersect, I have my point. So the last one is 6. So 6, I'll draw a line here. You are really looking for that intersection. All right, now 6, where does it meet this one? 0.0026. So I'll look for 0.0026. Where is it? 0.0026 should be, this is 2526 should be somewhere here. So I'm gonna draw a line. .0026. This is where they meet, and then I have my point there. Now let me go back and see if I can find a minus 0.2. So this is this is 0 minus 25, which means minus 0.2 is somewhere here. So I'll draw a line. Now if I have to include this one, I'll draw a line down here. All the way. And I know this one goes with 5. So I'll make an intersection there. So immediately, if you look at the data itself, we see that the 0.0026 is just too far from the other data. So what you do is, I would ignore that one. So the next phase is to draw the best fit line. So for you to draw the best fit line, if there is a data point that you want to ignore, you get rid of it. Like, we are not going to include this one in our best fit line. So this one is excluded from the best fit line. So I'll just say excluded. It is like an outlier. Now, if I have to draw a line, I'll use these points, this point all the way to here. So let me see if I can use my ruler on this one to draw a line, if it's possible at all. I just need to move this. Yeah, I think I can. All right, let me see. So maybe let me get rid of the best fit line and draw another one that makes a lot of sense. Alright, so I'm trying to make sure that I want to draw a straight line, and the straight line it doesn't necessarily need to touch all the points. It just needs to have similar points from both sides. That's what the best fit line is about. So although it doesn't look like a straight line because of the ruler I'm using, but I've tried as much as possible to capture the points. You can see that some points are not on the line. Like this point is not on the line. It doesn't matter. This point is the other side of the line. So in my head, I calculated that I think from this side I should have a point that is not on the line, and from this side I should have a point that is not on the line. But these three, this one, and this one, should be on the line. That's what the best fit line about. You don't follow points, but you look at your points and say which line represents all these points. That's what is important. Now, once you get your line, now search for points where you have intersection, where your line is passing through an intersection. Those are very important points. Like in this case, this point is passing through this intersection. So I will say I will select this point for my slope. So I just say I'm selecting this point for my slope. Then look for another point that is also passing through an intersection. If you can't find the point, that's fine, but try to, as much as possible, to find that point. So let me see if I can find another point passing through an intersection. I can't find any. Let me see. Although this is we can't find another point, but let me take this point. So I'll use this point for my slope. So once you select the 2 points, you need to connect them. So like how do you connect them? You draw a line from this point all the way down. Down to the other point. And then you draw a line also on this point all the way to this intersection. So in terms of the points that will give us a slope, this point, and this point, they will give us that triangle. So using that triangle, the 2 points here, this point and this point, will give us what we call rise. This point and this point will give us run. Now, how do you get rise? So what you do is you draw a line from here all the way to touch here and give this figure a value. So I'll give this figure a value. This is close to 6. So 5, 5.25, 5.5, 5.75, 5.8. So I'll call this one 5.8. So that is the top part of the rise. And then I'll go here all the way to here. So this is 1. So this is 1.0. So my rise is 5.8 minus 1.0. That is the rise. Now I'll come back here to find values for run. So if I draw a line from here, remember these are our 2 points that will give us the slope. I draw a line from here. This is 0.005. So this one is 0.00475. That is this point. So we go also to this point all the way down and see what the value is. This point here is 0.0035. So I'll just say this point is 0.0035. So our okay, so we are going down here. Okay, let me just make some correction. So this is a descending graph. So since it's a descending graph, it should be 1.0 because it's a descending graph. We are starting from 5, we are ending with 1. This is initial point we are starting, this is the final point we are starting. So if it is like y, this is y1, y2. So 1 is y2. So we start y2 minus y1. 1.0 minus 5.8. In terms of x, this one is x1, this one is x2. So we are going to start with this one. So 0.00475 minus 0.0035. So in terms of slope, we have 1 minus 5.8. So minus 4.8 divided by 0.00475 minus 0.0035. 0.00125. So 4.8 minus 4.8 divided by 0.00125. So for this one, the answer is minus 3840. So our slope is equal to negative 3840. Now, but at the beginning, we said that delta H is equal to minus r times slope. So in this case, it's minus 8.314 times the slope that we have there, minus 3840 joules. Because we are finding energy, the units are joules. So the negatives are going to cancel each other. We just need to multiply 8.314 times 3840. In that case, we get 31 926 joules. So enthalpy of vaporization is given in kilojoules. So we will say in the end that delta H vaporization is equal to 31.9 kilojoules per mole. So I'll also add more here. So that's how we use the graph to determine enthalpy of vaporization. It goes through a lot of processes. So just try to study this and find if you can do this on your homework assignment and also on the next question. Thank you.